Welcome everybody. Welcome to the lunch lecture of Van Rossum about Wonderwoods. We have Steven Schoenmakers with us, who will present this amazing project. So the floor is yours, Steven.
Thank you. Thanks for the introduction. Welcome all of you. Today I will first introduce myself, introduce Van Rossum to you who don't know it yet. Then we'll get into Wonderwoods, the main project for today, the load-bearing structure and some unique aspects of the project. Well, first me, I'm Steven Schoenmakers, working at Van Rossum Raadgevende Ingenieurs. For myself, I work at the office in Rotterdam and I started working here in 2012 after my study at the University in Eindhoven, where I studied 6 years from 2007 to 2012 and had a great time at KOers as well. So I'm hoping it's still as much fun as it was. And I'm one of the structural engineers of the Wonderwoods project. I started working on it at the early phases of the preliminary design, and I'm still working on it while right now we're starting with the realization phase of the project. So as Van Rossum, we are a structural engineering firm who's based in Amsterdam with our main office, and we have other offices in Rotterdam, Utrecht, and Almere. Where we have our main focus on utility and housing projects. There's not the infrastructural projects, but more of the buildings. And we only focused on the structural design of buildings and no other disciplines in Van Rossum. This is what I already indicated. 4 offices in Netherlands, mainly focused in the Randstad, but we're also doing quite a lot of projects outside there. As you can see, our biggest office is located in Amsterdam with over 90 people there, and the other offices are slightly smaller. We exist since 1953, and we've tried to focus on regular client-customer relationships. So we have a partnership with the architects or clients that we work with to know what we expect from each other. So our clients know what to expect from us and we can know what to expect from them. And in this way, we are able to work on a lot of challenging projects and nice structural designing projects. As you can see already a few here, this is Hoog Catharijne in Utrecht. And here's some more of the projects you might know from us. I think we've shown all these before to you at KOers over the years, but feel free to see more of them at our website. And as for me, I started working here already 8 years ago. Feels a lot less. We have a young team with a lot of young, enthusiastic people, structural engineers, BIM modelers, and all other disciplines in the office where we work on all kinds of different structural design projects, from more complex high-rise structures, as we can see here on the right, to the more smaller projects as schools or housing, which also have their own challenges. And the variety of projects is something I really like to do and to work on here. Well, that's a bit in a nutshell about Van Rossum. Today I'm here to show you something about Wonderwoods. Wonderwoods is a project being realized in Utrecht, and this gives an impression of the project already. It's a green project with a lot of trees and plants, and the architects tried to get the green forest into the city center of Utrecht with these 2 buildings. So I mentioned already, and you could see it a bit on the previous picture as well. Wonderwoods actually consists of 2 buildings, 2 towers. As we can see here in the far end, it's the first tower, and then here more in the front, the second tower. The first tower is the tower we call the Bueri Tower, which is designed by the architect Bueri from Italy. And the second tower is a MVSA tower, designed by the architect MVSA. And they are both situated on one single-story basement where parking is being realized. So there's 2 different architects for the 2 towers, but as a structural engineer, we do both of the towers together. In the towers, high-end apartments will be realized, but also offices and more commercial functions as horeca, restaurants and cafes and bars, and more of a museum function. And the housing that will be realized in the 2 towers are both rental and owner occupied, depending on the position in the tower. So I mentioned already, Bueri designed one of the towers. It's the Italian architect. We'll get later back into the architect Bueri itself. And he's supported by a Dutch architect, Imbo, for the more and now I'm looking for the English word. More, how will we call it in English? Wel, het uitwerken van de bouwkundige plattegronden en details. The Wonderwoods project is actually starting next week to be being built, and it's being built by the contractor Boele, situated in Rijswijk. If we look at our own team inside from Rossum, we work on the project with the project leader, project engineer leader, who does the overview of the whole project, and then we basically have a team for each tower. So 2 structural engineers for each tower and 2 draftsmen for each tower. However, of course, there's quite some interaction between the 2 different projects, not only because of the basement, but also on more higher levels, there's some interaction between the towers. So the teams work closely together. And next to this core team, of course, quite some other colleagues are involved as well. If there's some of the design challenges to be solved with quite specific. So a bit of the timeline of the Wonderwoods project. The design started in July 2018, where we started with the first phases and sketches of the towers. And over in 1.5 years, the technical design was made, and the idea for the tower was finished, and the contractor was selected to build this technical design. After this technical design, we had an optimization phase, and well, in a short while, they will start building on site with the first works for the building pit. And this year, the first piles for the building should be installed on site. Then the building time will be approximately 3.5 years to finish the whole building. But of course, the structure will be finished quite something before that, and then they have still time for the finishing of the building. This is a aerial overview of the Wonderwoods project, with the orange dot indicating the location of the building next to the jaarbeurs, and in the back we can see the railway station, and next to it the Galaxy Tower as well, which is currently being built. One of our other projects there. So this is the separation of the 2 towers, as I already mentioned. 2 towers from 2 different architects, and I will get into both of the towers later on in this presentation. The 2 towers are connected on ground floor level via just the deck of the basement. And there's a public roof terrace on the 6th floor of both of the buildings. And this roof terrace of the buildings is connected via a bridge in between the buildings. So you can walk from the roof terrace of the Bueri Tower to the roof terrace of the MVSA Tower. Well, first the Bueri Tower. This is the highest tower of the 2. This one will be slightly over 100 meters. In the building, there will be commercial spaces at the first levels. So up until the 6th story, there are offices and commercial spaces. And on top of this 6th story, there's the roof terrace, which is publicly accessible as long as you go to the restaurant, which is there on the 6th floor as well. And from this level upwards, there will be apartments being realized in the tower. The first level is the rental, and more to the top, owner occupied, so the apartments will be sold. Well, and the design of the Wonderwoods Tower might be familiar to you, because it's inspired by one of the other towers designed by this architect Stefano Bueri. This one in Milano, in Italy, which is called Vertical Forest. But you might also know I think I missed it here, but also in Eindhoven, of course, there's the Vertical Forest being realized at Stripe S by the same architect with the same concept of the green facades with plants and trees growing all there over the facade. So if we look more in the design of the Bueri Tower, this is a plan view of the top levels. I think this will be the 9th or the 10th floor, but if we go back a bit, we can see the top levels have the same structural principle. So all the housing apartments levels have the same structural principle, and below we have a different structural principle. The housing levels are realized by a concrete structure where we have concrete floors and concrete walls, cast on side walls, and some prefab facades on the sides. The floor spans from wall to wall. Underneath, basically, we have the same principle: load-bearing walls with floors spanning from wall to wall. But then a lot larger plot area due to the size of the building. If you look back at the top floors where the housing is realized, the walls are not only used for vertical load bearing, but also for the stability. And then the side facades are also load bearing, but they do not act in the stability system of the tower. And this picture not only indicates the vertical load distribution, but it also shows how the green plants and green trees are organized around the tower. So where in the impressions, the green looks quite random, in reality, the green is not random at all. It's quite strictly ordered. So in the extension of load-bearing walls, trees can be realized. We can create a tree pot, tree planter to plant a tree, and the regular plants are realized in the extension of floor slabs and in the extension of balconies. The trees can be in every extension of every wall, but can never be on another place. So for example, here on the sides, we will never see one of the trees occurring since there's no load bearing there. The difference here, we see some trees at the edges. That's because this is the plot of the roof terrace as well. So basically underneath this tree, there's a load-bearing wall as well again. And when we have a tree on this level, on this position, it might be on the next few levels that the tree jumps to the next grid line and will be on this position. So to find out how to work with these trees in the design of the tower, a wind tunnel test was carried out to find the forces on the trees and from the trees back on the building. So there was a mock-up of the Bueri Tower made, and it was tested in a wind tunnel. This one was carried out in Germany, where on all the positions of the trees, measure points were made, as we can see here at the bottom images, and all these dots indicate where the trees are being realized now. And as you can see already a bit by the colors, there's quite some deviation in the amount of wind load on each tree. The trees on the edges carry a lot more wind load than the more in the center of the building. Well, and this wind tunnel test was used to design the tree connections to the building itself. This image shows the tree pods. I should explain it a bit to show you how it works. Here we have a top view of a tree pot, which is basically the gray outline here. And the tree pot is placed on a console, which is attached to the load-bearing wall. So the red line here indicates the console, which is basically the load-bearing part for the tree. And then this tree pot is placed on the console and horizontally supported on the two sides with a small concrete block to the floor slab. Well, this is a side view. The blue line indicates the opstort, as we call it in Dutch, to support the tree pot sideways so it doesn't fall over. And in the floor thickness, the console is being realized, as we can see it here in the top view again. And the tree pot is then connected on the on the 4 dots here, so to take the wind moments into account and being brought back to the main load bearing structure behind there. Well, in this tree pod, which we see here on the right in a slightly 3D impression, we have the tree itself, which is then connected again. Well, the tree grows in the earth, which is in the pod, but is also connected via cables to prevent it from falling down. And actually, there's a 3-way connection. So firstly, and then I go back to Dutch again, the kluit van de boom. So the bottom of the tree should withhold itself in the tree pod so it doesn't fall over. Then we have a second connection, which is indicated in red, to prevent the tree, if the kluit van de boom fails, the tree will always still be hanging on these 3 cables to prevent it from falling down. And then we have a final connection of the tree, which is indicated in pink here. And this is again a steel cable, but this one comes out of the ground area and is just next to the tree, which goes then to the ceiling here on top. And this pink cable should prevent the tree from falling down if the core of the tree snaps. So if there might be some high wind loads on the trees and the core will break, the tree will always be hung in this pink cable so it doesn't fall down on the ground floors. That's to keep it safe, since it could be otherwise falling down. So that's for the tree pods. The planters itself, for the regular plants, they're connected to the edge of the floor slabs. Little bit less complex, since it doesn't catch that much wind, of course, due to the size, and also the weight of the ground. The earth cover is a lot less there. I didn't put any images of that in the presentation, since it's a bit more simple to connect them to the floor slabs. So I want to move forward to the MVSA tower, where the MVSA tower has a bit more functions in it than just the 2 functions as we saw at the Bueri tower. For MVSA, we have a ground floor multi-flexible usage of the space, so it should be a really open space where a museum can be realized. And on top of that, offices are realized. And these offices should always be possible in the future to also realize these offices at the first 2 floors. And besides these offices and museum function at the ground floors, also some housing is being designed there at one of the sides of the building. I will show that later on. Then on top of the offices, we have a public roof terrace again, which is connected to the Bueri roof terrace. And above the roof terrace, then we have mostly housing, apartments again, but still some offices as well, which are being built next to the housing. I will show that also later on in the section, how it works. So in the MVSA tower, the ground floor is a flexible space where we have an open structure. And here we see the principle of this open structure. We have columns with beams in the floor height, where hollow core slabs are spanning from beam. We use here steel members to be able to make the beams in the same height as the floors itself, so there's no structure underneath the floor height. And this was for maximum flexibility for the museum, which will be realized here. Also, one of the demands for this museum and the future flexibility was that on each floor position, a new void must be able to be made in the future. So on every position, between the 4 grid lines, basically, all the floor plates should be able to be taken out, so that we create a new void on that place. So, and that should be completely random for the next tenants. If they want a void, for example, here in this position, this whole area of floor slabs should be able to be taken out of the structure. So it's slightly modular what we build there, but it gives quite some extra demands for the structure. For example, all the columns should therefore be able to have a buckling length of 2 levels high instead of 1. Because if we would take out all the floor slabs around the column would be freestanding over 2 levels, instead of the single level, which it is now in the starting of the building. Also on this picture of the first floors, we see that the museum is realized at this area, which I'm indicating now. I hope you can see it. And next to the museum, some housing is realized. This is on this side. So quite some strict demands for the sound isolation of the housing to the next to the museums. And then we can see a big void here. That is where an atrium is realized with some extra green in it, green plants and a lot of trees there. The museum that's being realized in this MVSA tower is called the Play Lab. It's currently open in Tokyo, and it's actually it gives it gives open spaces where they have light shows, light and sound shows, as is bits illustrated on this picture. So there's no real physical art there. They make the art with the light shows that they give there. And on top of this museum, there's an office planned. So from the 3rd to the 6th floor, they plan to make new offices, as we can see a bit on this floor plan. And also these offices should have the feeling of a real green part. So the forest is taken into the city and the forest is taken into the offices. And therefore, on each of the floors of each of the office floors, as we call it in Dutch, wintertuinen are being realized. Here it shows an impression of such a garden, which is then made in the office space. So again, some trees which are being planted in the wintertuin, and they are at various locations. For example, on this floor, they are well, as we can see here, the white spots. But on the next floor, it might be just next to for the next two grid lines, or just another random position. The wintertuinen are always realized on the facade of the building, and that's because of the plants need the light from the facade. We weren't able to make them more inside due to the light that the plants need. Then on top of the offices, we have a roof terrace, which is at the 6th floor again, and it shows already a lot of trees there again. So a lot of extra load on the structure to make these trees be able to grow in the earth that they need. And this picture also already shows what is going on above the offices. So at this level, the office is stopped and housing is being realized on top of the offices. So this part of the building is all housing. But next to the housing, there's still some offices being continued to the 13th floor. And in a plan view, it looks like this. So here on the right side, we have the housing with on each grid another house, so another apartment. So we have an apartment between the load-bearing walls, and then again one on the facade, two on the facade here actually. And next to the housing part, the offices are still being built. So here on the left, we see the part where the offices are realized. There's no connection between the housing and the offices. So there's just a closed concrete wall between them. Of course, for the sound isolation, the wall is there, but also to prevent any connection possible. So no one can walk from his apartment to the offices or vice versa, also not via the stairs. In a section, it actually looks like this. So on the left side, again, we have the offices which are being built there. On the right side, the apartments. And as you can see, the floor height of the offices is larger than the floor height of the housing. So where we have here on the right side 7 levels of apartments, on the left side we have only 6 levels of offices. And that's because of the demands for installations. The offices need a lot more recirculation of the air, so a lot more fresh air. And these air vents need some height at the office floors. So there's basically a reservation in height, in story height, for the installations to blow in the fresh air there. And you might have seen it before already on some other plans, but these office floors are hollow core slabs which span from facade to the next grid line where we have a beam to support them. We chose to make locally a steel member in the floor height to be able to put all the air vents underneath the hollow core slab from one part of the floor to the next part of the floor. And next to the steel members, there's more cheaper concrete members. So basically cost efficient is to create the concrete members here. But the air vents cannot pass these concrete members, of course, since they are enormous. So therefore we varied in concrete members where it is possible, and where it's not possible, we made over one grid line steel member to be able to pass with the installations. Now these two towers are on one parking garage, so one basement with parking. And here on the right side, the Bueri Tower is being founded on the piles we see in this area, and on the left side, the MVSA Tower. And as you can already see, there's a lot more piles underneath Bueri than underneath MVSA, and that's because of the, well, of course, the height. The Bueri Tower is 30 meters higher, so there's a lot more concrete there, but also the structure of the MVSA Tower of the office part is a lot lighter than the Bueri Tower, which is all solid and massive in concrete, and the MVSA Tower uses steel construction and hollow core slabs. So there's a lot more piles and a lot more weight underneath the Bueri Tower. And during the design phases of the tower, we work with the geotechnical advisor, which is KOers Engineering for this project. And the geotechnical advisor started with a settlement analysis, a settlement calculation. And here on the top, we see the images that KOers, the geotechnical advisor, made of the settlements of the two buildings that we expect. So based on the dead load of the building, so just the weight on the building, if we would put that there on the Maiveld, which is there, we expect that the Bueri Tower, which is still on the right, would settle 120 millimeters down. So the center of the building will just move downwards in time with over 10 centimeters. While the MVSA Tower, the deflections over time, or the displacements over time, are a lot less, only 50 millimeters. And here we can see it more in the graph. It's a bit more clear. Settlements of the Bueri Tower, and then you should look at the blue line, which is the finalized building, will settle nearly 3 times the amount of the MVSA Tower. So there's a lot of settle differences there underneath the building. So as you can also see in this graph at the bottom, the deflections at the center of the building and of the edge of the building are a lot different. So there's a lot of settlement differences from the edge to the building to the core of the building. And with this amount of deflections or settlements underneath the building, it would give enormous problems in the building for both installations in it. You can imagine if there's a sewer going out of the building, you would need to pump it up, because you would need to pump the sewer water over 100 millimeters upwards to go out. And next to that, also the structure would need to be able to follow these deflections differences. So a concrete floor slab would need to be able to follow this settlement of nearly 10 or over 10 centimeters. And that's a lot for the concrete floors, of course, not to speak of the comfort, which is gone. You can imagine if you walk in the building and you walk from the facade to the core, if you walk down 10 centimeters, there's no comfort. You would lose any comfort at all. So we worked with the geotechnical advisor, and we created our own soil interaction calculation model, where we used our building calculation models and integrated the soil in this calculations of the building. And this is a scheme how we made it. So on top here, we can see basically a schematization of the building with the foundation of the building. And what we normally do for a regular project, we basically stop at the basement, we model some supports underneath the basement, and that's it. So with some piles underneath the basement, and we're finished with our calculation model, and we check the building and make sure the building works. So here the deflections were too much, so we also modeled the ground slab where the piles are being founded. So this is the ground slab, which is at 15 meters minus NAP, and it has a certain stiffness to withstand these piles, but also this floor slab, or this soil slab, excuse me, will settle down in time. That's what we saw on the previous pictures. In between this building and the soil slab, the piles are being modeled. And this whole model simulates both building and the soil slab. And the reason to do this is to take into account that the building has a certain stiffness that will spread loads more outward than if we make just a geotechnical calculation where we put only a dead load on the soil slab, basically. So here you results of this calculations of the settlements analysis, which we did with the ground interaction model. I primarily focus now on the Bueri Tower. As you can see, by taking into account the stiffness of the building, the load is being spread further out. So the spot with the largest deflections, so here the dark blue spot, it's larger than we saw previously in the geotechnical calculations, but the amount of deflections is a lot smaller here. So if we take into account the stiffness of the building, the deflections are only 60 millimeters or 58 millimeters. And it's being spread a bit more outwards. So what we see that the building actually does is once the soil underneath the core starts to settle a bit, the building spreads the load by itself a bit more to the side, since it has the stiffness in the building itself. And by doing this, we were able to reduce the deflections to 60 millimeters at the core of the building. And at the edge of the building, the deflections are nearly 30 millimeters, which gives a deflection difference of over 30 millimeters over 20 meter. And these are more acceptable differences. And we can solve these kind of differences in the structure itself. We can reinforce the concrete slabs for these settlement differences. We can make this work in the building. And also for installations, these kinds of differences are acceptable, and we don't expect any damages from this in the future. But also to prevent this, the 60 millimeters from happening in realization phase, during the building, we will build the building slightly higher at the core to, so once it's settled in, that it will end up on a horizontal line. So therefore, yeah, we made some building phase calculations where the core is being built up slightly higher, and we see that in the end it will eventually end up horizontally. So that is what I wanted to show you about the Wonderwoods project. I think it went quite fast, so feel free to ask any questions further on. Well, of course, once you're finished with the university, feel free to contact us. We're always looking for talented structural engineers. So look at our website. You can find our vacatures there, but also feel free to do an open solicitation. That's what I wanted to tell you about the Wonderwoods project. I didn't see any questions in the chat during the presentation, but there might be a lot now. So I think it is easiest if we use the raise hand option in Teams, so we can do it one by one. Yes, I can see only the last name, but Brinkhoff?
Yeah, that's me, Michael. Hi.
Hi.
It's not necessarily a, well, sort of a structural engineering question, but do you know how much concrete they used for this if you would compare it to a equivalent building without all the trees?
It's a good question. No, I don't have it present at the moment, but we do have an estimation of the weight of only the trees and the earth. So and I don't have it present as well, but it's quite a lot. It's I think it was 15 or 20% of the weight is just the earth and the plants. And that's of course therefore we require extra piles in the foundation and of course some extra concrete in the building. We thickened the floors to be able to make these roof terraces. So yeah, it's an interesting question, but I don't have the answer here.
So would you then say it's a sustainable building?
Good question. Well, of course, creating all these trees at these high levels requires some extra material, but it's a good way to get the green in the city center. What we normally see is there's green at ground floor level, but not at higher levels in the buildings or in the towers. So to create these healthy offices, which they try to make here, well, at least it's a good option to do it this way. But if it's really sustainable because of the extra material we need, it's a good question.
All right, thanks.
Yes, Mike Veenhuis.
Yes, I don't know if you said this, but with what kind of team do you work on this project? Like what size and how is the organization done within a team with such a massive project?
Well, from us as a structural engineer, we work with I think in total 9 of us on the project. So 2 structural engineers per tower and 2 draftsmen per tower. So for a normal project like this would be 4 or 5 persons for each tower. Since these are basically 2 towers, we enlarge the team slightly. We work with a quite young team on the project as well. So we have, I think last year, Gerben van der Meijden showed you a presentation about Sluishuis. He's now also working on this project. So on the Wonderwoods project, he's combining it with Sluishuis now. And we have some more young structural engineers working on it. A few from Eindhoven actually, and also some from Delft. And then also 4 draftsmen, which are making the BIM model of the project and doing the 2D work. So compared to the architects, we have always a relative small team, and we at Van Rossum try to maintain a compact team on a project, so everyone in the project team is aware of what's going on in the project. So you don't do just one part of the building. If you work on a project, you work on the whole project. So not just one floor or calculate this one floor reinforcement. We want everyone involved in the project to know about the whole project, so we get involved with everything which is going on. Other questions from you? I don't see any other questions coming up.
If there are no more questions, I would like to thank you, Steven Schoemaker, for giving this very interesting lunch lecture about Wonderwoods. Also the rest, thank you for attending this lunch lecture. And next week we have another online COCO, and then week after that we have another lunch lecture. Please check them out on the site. And I wish you all a very nice afternoon. Thank you.